Welcome everyone to week 14, lecture number 1 on fundamental of econometrics, the undergrad course 4. We are in chapter 6 and we were discussing autocorrelation, regression diagnostic part 3 of the econometrics by example by Gujarati. Week 14 course is based on remedial measures for autocorrelation, namely the first difference, and then we are going to talk about model evaluation and we are going to summarize and conclude this chapter. But before starting the content of week 14, I would like to give you a quick overview of the last two lectures on autocorrelation so that we can link the theory which we have studied already with what we have to do today. Autocorrelation is a case when we have a problem of successive value of error term of the model being correlated with one another. We get a problem of autocorrelation, and we did discuss that when this autocorrelation problem happens, it causes our OLS estimator being not blue anymore, and their variance is not anymore the best. Secondly, we did also discuss the causes of autocorrelation, and we saw all these in detail. So in a very previous lecture, we did discuss the test for detecting the autocorrelation. We did talk about the graphical method, that how the two approaches through graphical method can guide us for presence or absence of autocorrelation. Namely, we plotted the residual term chronologically, or we also use the error term being plotted against its lag value for possible presence of autocorrelation. We did saw that if there is a pattern for these two graphs, it will indicate the presence of autocorrelation. We also talked about the run test, and I told you that the run test is a kind of like looking into more formally the graphical approach. In this, we look into the pattern of the sequence of the residual terms and their possible signs. If it's following, if the sequence of the residual values follow more runs or less runs, then it could be a possible indication of autocorrelation. We learn how we can construct a confidence interval, and if the number of runs are within that interval, it will indicate that there is no autocorrelation. Otherwise, it could be a positive or negative autocorrelation. Then we did talked about Durbin-Watson D-statistic test, and we saw their assumption, the critical region for it, and how this test works, and how if the value is equal to 2 represent, or closer to 2 represent no autocorrelation. If the value is 0 or close to 0, it represent positive autocorrelation, and if a value is 4 or close to 4 for D statistic, then it can be an indication of a negative autocorrelation. We also discussed the Brish and Godfrey or BGLM test as well. We also saw the application of all these tests in Eviews, and by this stage now I presume that we are in a position to detect autocorrelation in our data. And finally, to mention from the previous class that the first two methods on this slide are more of ad hoc nature, whereas the later two methods are the methods which you are supposed to learn in more detail, and would strongly recommend the application of one of these methods for detecting autocorrelation in your data. Now at this stage, I presume that you are ready to proceed and solve the problem of autocorrelation using some remedial measures that the textbooks recommends us to do use. So in week 4, we are going to focus on remedial measures. So let me start with the remedial measures of the autocorrelation. So if we talk about a remedial measure of autocorrelation, so we have to do that after once we diagnose that there is a problem of autocorrelation. So once we know that, we get confirmed using these tests which we discussed or we just summarized a while ago, that how if there is a problem of autocorrelation, now what should we do? So we have three options to fix the problem of autocorrelation. The first option is that we have to check if this autocorrelation is a pure autocorrelation. We have to confirm that is it a pure autocorrelation that's caused by some reasons of autocorrelation, or if it's autocorrelation because of the misspecification of the model. We already did discuss the causes of autocorrelation, in which we saw that if there is a misspecification of the model, it can lead to a problem of autocorrelation. So we first have to confirm if the model is correctly specified. If it's incorrectly specified, so that could lead a problem of autocorrelation. So before solving the problem, we have to be sure if this autocorrelation is because of misspecification of the model, or it's because of some other reasons which we have saw. So the question then do arise that how we can fix the problem of misspecification. So at this stage, all I could tell you is that we can reconsider the model for checking if all relevant variables are included in the model, because we saw that misspecification of the model by excluding a relevant variable could cause a problem of autocorrelation. So when we drop a relevant variable, it may lead to a problem of autocorrelation. So we need to reconsider our model and check if we haven't dropped a very relevant variable. Reconsidering the model for checking if there is no irrelevant variable in the model, that's also misspecification error if you include irrelevant variable, or if you are defining a linear relationship being non-linear, or having non-linear relationship being modeled as linearly. All these may lead to a problem of autocorrelation. So you better to check for that correct functional form. Make sure that all relevant variables are included. How we can do all that, there is a separate topic on that, so I will do that later once we cover all the remedial measure of the autocorrelation. So for time being, I will leave this discussion inconclusive at this stage, just summarizing it, that if the autocorrelation is because of the misspecification bias, you have to be sure if it's because of the misspecification of the model, you better to fix that. So once you are sure that your autocorrelation is not because of the specification bias, then you are sure that it's a pure autocorrelation. So pure autocorrelation can be solved through transforming the original model, and that transform model then no more have the problem of autocorrelation. We're gonna see that how it works in bigger data. When we have very large sample size, we can also use Newey-West method that can fix the problem of autocorrelation by providing us the standard error OLS estimator corrected for autocorrelation. So it's comparable to the white test, the white procedure which we have studied for fixing the problem of heteroscedasticity while obtaining the heteroscedastic corrected standard error. So Newey-West method is comparable to the white method for heteroscedasticity, but like white method, it's also valid only for large samples. So for small samples, we still have to do the transformation, and how we do that, I will show you in a minute. In some situation, when there is a minor problem of autocorrelation, we can still continue with using the OLS method because it wouldn't affect the things too much. So to sum it up, there are three possible ways through which we can proceed once we identify that there is a problem of autocorrelation. The first way is that we have to be sure that the autocorrelation is not because of the misspecification bias. If there is a misspecification in the model, we better to fix that and then check for autocorrelation. If autocorrelation is not because of the misspecification bias, or which we call the pure autocorrelation, in that case we have two options. Either we use a transformation of our original model to a model which do not have problem of autocorrelation, but that's more valid for the small sample sizes. In larger sample size, we can use a Newey-West method to obtain the standard error of OLS estimator, and these standard error are corrected for autocorrelation. So these are the two options if we have a pure autocorrelation, or the autocorrelation not because of the specification problem. And then we have the third case in which we can still use OLS method when the problem of autocorrelation is minor, of a minute nature. So we have to discuss a small background before going for the remedial measure, but going there to the background, I would like to emphasize that in the remedial measure, we are focused on the remedial measure for pure autocorrelation. I am not including the first option in this discussion for the reason that we have to cover that once we cover the entire topic of autocorrelation. So please be informed that the discussion from this point onward is focused on only discussing the problem of pure autocorrelation, or the autocorrelation caused because of the reasons other than the model misspecification. So with a small background, I would like to remind you again that once we have the problem of autocorrelation, our OLS estimators are not blue, so we cannot trust the OLS procedure or the hypothesis testing mechanism which we do perform once we apply OLS, until and unless we fix the problem of autocorrelation. So how we can fix this problem? We can start with a very simple example to understand the procedure of fixing the problem of autocorrelation. This simple model is based on one regressor x2 and then y variable yt being regressed on x2. Both are time series variable, and we suspect that the error term of this model is regressive of order 1, or it follows AR1 procedure as have been shown here. UT is equal to being regressed on the row or the correlation coefficient value UT minus 1, the lag value of the error term, and then the ET refers to, this is epsilon. So basically epsilon T is refer to a residual term that's free of autocorrelation, or it has no more autocorrelation. So in simple word, I am assuming a model which have a problem of autocorrelation but of order 1, or follows the AR1 process. So how can we solve the problem of autocorrelation in this model? Let me follow a small procedure. I will try to explain each and every point. I hope you will get that simple procedure of fixing the problem of autocorrelation mathematically. So let me start with the same equation, same model which I have shown you a while ago. So the same model, y being regressed on the explanatory variable x2 with first order autoregressive u error term t. So now what we do is that I'm going to take the lag value of this model and I'm going to multiply it with the rho, or the correlation or the autocorrelation coefficient. So we have this relation being hold in time t, and we presume this relation hold also hold in time t minus 1 as well. So I'm taking that model yt minus 1 being regressed on x2 t minus 1 and then error term t minus 1, and I'm going to multiply the rho with this. So when I do that, I get equation number 2 in which I have rho yt minus 1 is equal to rho beta 1 plus rho beta 2 x2 t minus 1 plus rho ut minus 1. So that's equation 2. Now I'm going to subtract equation 2 from equation 1. So someone may ask this question, why we should be doing all this process? So I will hold this discussion or this mathematical transformation. So I will hold this mathematical transformation at this stage, and first let me tell you the logic of applying this method. So this was the model with which we started, and we presume that it is suffered from first order autocorrelation. So by definition, epsilon is not correlated with its previous value, or I just to mention it that Since this model error term is just correlated with its previous value, so what we did is that we took a model of error term being regress on its previous value, and then it has an error as well, but this error is no more autocorrelated. So if I take this second equation, ut is equal to rho ut minus 1 plus epsilon t, and I kind of rewrite this equation. So epsilon t is equal to error term t minus rho ut minus 1. So I just rewrote the original equation, or you can say I transform this equation to this equation by just taking this term or leaving this term at its place, but moving this to the other side of the equation. So this gives me a new equation. And if you look at this, what does this show? This error term epsilon t is not autocorrelated. So in another word, we can obtain a autocorrelation free error term if we subtract from the error term its lag value multiplied by the value of the autocorrelation coefficient. So that's the conclusion, or that's the logic, and that's what I have written here. The new error term epsilon is no more correlated with its lag. Why this happens? Because a product of autocorrelation coefficient and the lag value of autocorrelated error term ut minus 1 is subtracted from the error term values. So this lead me to a very simple lesson, and that lesson is that if you have the autocorrelation of order 1 and you multiply the lag value of error term with the value of autocorrelation coefficient and it's subtracted from the original error term, you get a autocorrelation free error term, or in other words, you get the error term that are no more correlated with its previous or lag value. So having this lesson, coming back to this point, while subtracting equation 2 from equation 1, actually I am ensuring that I subtract the error term you multiply with, or in other words, when I am doing that, I am ensuring to subtract this term from this term, and that will give me the same transformation which will ensure the presence of no autocorrelation. Let me demonstrate it, that would make it more clear. So this is my equation 1, yt is equal to b1 plus b2 x2 t plus ut. That's the equation from where we started. And equation 2 is the second equation which I generated by taking the log of the lag values of the first equation and multiplying it with the autocorrelation coefficient, or the rho. So when I subtract these two, I put the negative sign for simplicity, and then you can see I can summarize this equation: yt minus rho yt minus 1, that should be equal to beta 1 minus beta 1 with multiply with rho. Let me take my pen so that I can mark them. So this beta 1 and this beta 1 minus 1, then you have plus, so plus, then beta 2 x2, this minus rho beta 2 x2, so beta 2 x2 minus rho beta 2 x2 t minus 1, then plus ut error term and minus rho, so plus error term and then minus rho ut minus 1. So that's what you obtain when you subtract equation 2 from equation 1. And then we do some simplification, for example, by taking beta 1 common here, by taking beta 2 common here. So we can write this equation as beta 1 into 1 minus rho plus beta 2 into x2 minus rho x2 t minus 1 plus error term. And now look at this term. We already saw that we define an equation in which we say that residual terms is of order 1, or we saw this transformation already, or we already saw that error term is equal to ut minus ut minus 1. So we saw this transformation already, so I can use this error term here. So instead of using original ut, we replace this to epsilon t, and this epsilon t is now autocorrelation free. So in other words, we did the same mechanism which I just explained on the separate slide, that when you multiply the lag value of the residual with the autocorrelation coefficient and you subtract that product from the original residual, you get a residual value that's no more autocorrelated. So hence the model which we obtain by this transformation is autocorrelation free. So let me take this model to the next slide and let me describe a few of the property of this model. So this is the model which we just obtained. This equation can be summarized further when we write it as yt steric equal to beta 1 steric plus beta 2 x2 steric plus the epsilon term. So this term is y steric, this term is beta 1 steric, and this term is beta 2 steric, x2 steric. So this one is beta 1 steric and this one is yt steric. So we have this new transform model. Now this transform model has some very interesting properties. First of all, if we apply OLS to this model, this is no more a simple OLS method. We call it generalized least square method. So GLS, generalized least square method, GLS. You have to note a few more things. This is also called generalized quasi or difference equation model. This is there are a number of names given to it, but we will stick to this name, difference equation model. So why we call it difference equation model? Because this yt steric is equal to the difference of the y variable. Like you are subtracting yt minus, for example, if I ignore the value of rho, so yt minus 1 is the difference between the y variable with its lag value. Similarly, x variable also shows, x steric shows that this is the difference between x2 variable and its first lag variable. For time being, I'm ignoring the rho. The important point is that this model is now, this transform model, this difference equation model is free from the problem of autocorrelation, because we already saw that the epsilon is no more correlated, or they are not correlated with its lag value. So the problem with this model or the challenge with this model, we have this transformation model, this form, the first form, or the both are same. These two are same model. The problem with this model is that we don't know the value of rho. Yes, this whole transformation is based on a simple logic that you took the rho value, you multiply it with its lag model, and then you subtract the original, you subtract this transformed model from the original model. So you got an epsilon that is no more autocorrelated, but the problem is you don't have the rho value. So if you don't have the value of rho, what should you do? Again, we stick to some educated guesses for the value of rho, and through that we we do this transformation, and that solves the problem of autocorrelation. So that was the theory, that was the background, and now I will start. But before starting, let me give you the summary. The summary of the background is that we can solve the problem of autocorrelation by transforming our model and then applying the ordinary least square method, which we call generalized least square method. But this procedure is based on a simple assumption that we know the value of rho. So we took that value of rho, or the autocorrelation coefficient. we multiply it with its lag values, then we subtract the transform values from the original model. So the model which is in the difference form, if we take that model and we apply the GLS to it, this model is blue, the estimator from this model is blue. But the problem is that we don't know rho. So first we have to ensure that we get the rho value, and then we can solve the problem of autocorrelation. So the remedial measures for autocorrelation, I just explained you already that we in this discussion, in this entire lecture and the lecture to be followed, we are discussing the remedial measure for autocorrelation that is pure in nature, or in other words, the autocorrelation that is not caused by the specification of the misspecification of the model, or the wrong specification of the model. So we are just discussing the autocorrelation that's pure in nature. In that regard, we already saw that we can transform our model to fix the problem of pure autocorrelation and then apply ordinary least square method, which is then called generalized least square method, and we can solve the problem of autocorrelation. But for all that, we do not know the value of the rho or the autocorrelation coefficient, so we follow some guess ways through which we can find the rho value. So there are three methods through which we can guess this rho value and can use it for transforming our model to solve the problem of pure autocorrelation. These three methods are the first difference transformation, the rho based on the Durbin-Watson statistics, and the rho estimated from the residuals, and then the Newey-West method. That method is a direct method used for large sample and that ensure the blue OLS estimators through the direct estimation method. So first we are going to talk about the first three methods, and then we will move to the final method. So let me start with the first difference transformation. Let's start again with the background of the derivation which we just saw for transforming our model to the first difference model, or the difference model. We assume that there is a model with one dependent and one explanatory variables, and then we use that AR1 assumption of the least of the error term being correlated with only the previous value, and then we obtain this equation I just showed you a while ago. So now we are going to use this and to see that how we can do this first difference transformation to solve the problem of autocorrelation. The problem with this transformation, as we saw earlier, that we do not know the value of rho, but for time being, if we assume that we can think of certain value of rho. For example, if we assume that this rho could be equal to 1. Now what does rho equal to 1 mean? Rho equal to 1 mean that, let's say, the equation which we just wrote for the for this error term, rho equal to 1 mean here is that this rho error term and error term in t-1 period are perfectly positively correlated. So we are taking a specific case of positive autocorrelation, and we say that the autocorrelation between the rho term, the autocorrelation between the successive values of error term is equal to 1, or it's a perfect positive autocorrelation, or it's close to perfect positive autocorrelation. So in that case, we have the value of rho equal to 1. If we plug in that value in this equation, or this difference equation, we get a very interesting situation. Let me show you that when we plug in that value rho equal to 1, so yt minus 1 into yt minus 1, rho replaced by 1. Similarly, b1 into 1 minus 1, rho replaced by 1, plus b2 x2 minus 1 into x2 t-1, where rho is replaced again by 1, and the error term epsilon at its own place. So if you simplify that, you are left with yt minus 1, b1 becomes 0 because it's multiplied with 0, and b2 into x2t minus x2t minus 1 plus epsilon t. Now we can write yt minus 1 with some substitution. So we write yt minus 1 as delta yt, that's equal to beta 2, because beta 1 is 0 now, and then x2t minus x2t minus 1 with delta x2t plus then epsilon t. So now this model in the box is called first difference transformation. We call it first difference transformation because we took only subtracted the row from the first lag from the original model. There you can think of second and third transformations as well. We are not going to discuss or perform that here at this level, but there are possibility of having that. Now look at this transformation model. This is called the first difference model because the dependent variable is no more a single variable, rather it's the difference of the dependent variable, the difference of between the original value and its first lag. Similarly, the explanatory variable is also in the difference form. It's no more the explanatory variable having the value of the original variable, but original variable and then value of the lag being subtracted from it. So you got the first difference of the explanatory variable as well. So that's why it's called the first difference model. Now if we estimate this first difference model using ordinary least square method, this will ensure the blue parameter, or the blue estimated value, or the estimator from this OLS procedure would be blue, and it would be free from autocorrelation. But the problem with this transformation is that it's only valid if we have row equal to 1 or if it's close to 1. So this is important to note. Another interesting thing with this model is that we have no more an intercept term. If you look at the differences, we do not have the intercept term here. So if we run this model without intercept, that will solve the problem of autocorrelation. But if we include the intercept as well in this model, it cover up for trend in the model. Like if we have an autocorrelation in the data and there is trend as well, so if we use the first difference model along with trend, that may solve the problem of trend, linear trend as well in our data. So that's an added advantage of this mode transformation or first difference transformation. So we should keep that property of this first transformation in our mind as well while applying this method. Now moving back to my original slide, so we were discussing that the pure autocorrelation could be solved if we know the value of rho, and the rho value could be guessed through number of ways. We already saw that how we can use first difference transformation for the value of rho and can solve the problem of autocorrelation. Now we move to the second method, that in which we can guess the rho value based on Durbin-Watson D statistic. So for Durbin-Watson D statistic, first difference transformation, as we saw, we assume that its value is rho value is equal to 1, or if we have the rho value being equal to 1, then only we can use that method. However, we may have a situation in which rho value may not be equal to 1 or close to 1, so then that first difference transformation may not work good. So the alternative method for getting the rho value is then using the Durbin-Watson D statistic. How we can do that? You may already recall the equation, the functional, the Durbin-Watson D statistic test statistic, in which we says that dw is equal to 2 into 1 minus rho. If you rearrange this equation, you can easily see that rho is equal to 1 minus d over 2. So in principle, if we have the value of d, we can calculate the value of rho from there, and then once we have the value of rho, we can then transform the generalized difference by plugging in the value of rho from here to that model, and then we can apply the ordinary least square method and can obtain the blue estimator. So but be informed that this method only hold true if you have a large sample. For small samples, it doesn't work. So that was the case when you can use the Durbin-Watson D statistic for obtaining the value of rho and then using that rho value for transforming the original model and then applying ordinary least square method and solving the problem of autocorrelation. Then we think about the third method, which is the rho estimated from the residual. So let's try this one. This is the same procedure as we discussed while we were discussing the background material for transformation. So again, starting from the same model with one explanatory variable and then the dependent yt being regress on that x2t, and if we assume that there is AR1 process, then we can run the above model and we can use the error term, and being error term then regressing on the lag value of the error term. So if we run the original model, regress y on x, obtain the forecasted value of the error, and then use this forecasted value of the error and regress it on its lag value and obtain the coefficient of beta here from this model. So that would be the approximation for the rho value, and then you can use this rho value for transforming your original model and then use that for estimating the transforming the original data and then applying OLS and then ensure the blue estimator. So this procedure may also work. So going back to the original slide, we started our discussion from the point that we want to see the remedial measure for pure autocorrelation. Pure autocorrelation is the autocorrelation that does not happens because of the specification bias or model misspecification. We says that we can solve the problem of pure autocorrelation if we transform our model. This transformation then ensure the autocorrelation free OLS estimator, or we get blue estimator for these transformations. However, to perform this transformation, we require the value of autocorrelation coefficient rho, which is not known to us. Then we saw three ways through which we can find this rho. The first one was the first difference transformation, in which we assume if the rho value is equal to 1 or close to 1, then we can use this transformation. Then we saw the Durbin-Watson d-statistic based transformation, in which we use the d-statistic for approximating the value of rho and then using the transformation and ensuring the blue OLS estimators. Then we talked about using the residual of the original model for regressing it on the lag value of the error term and then obtaining the value of rho and then using it in the transformation of the model. So moving to the final method of remedial measure for autocorrelation, the Newey-West method. This method, before telling about this method, let me remind you that all the method which we have studied or discussed a while ago, all these methods are based on trial and error methods, and mostly the success of these methods depends on the nature of the problem and on the sample size. The nature of the problem refers to, for example, in the first difference transformation, we presume that the error terms are positively correlated, or rho value should be equal to 1, or the other method based on Durbin-Watson d-statistics requires a larger sample size. So the Newey-West method is a slightly different method. Rather than going on trial and error basis, this method by default ensure the ordinary least square method can be applied directly, and this method ensure that we obtain the standard error being corrected for the problem of autocorrelation, or in other words, the application of Newey and West method ensure the blue estimators from OLS methods directly without doing any transformation. However, this method is also valid for a very large sample size. Now there may be question that how Newey and West method ensure this blue estimators directly. There is a certain mechanism being attached in the background working, but as being students of management education, we are not concerned or we are not interested in that mechanism, all we have to do is to apply this method. So for that reasons we should know this, that there is a procedure which is called HAC procedure, that's heteroscedasticity and autocorrelation consistent procedure in software, that's called HAC. If you apply that procedure, that automatically ensure the autocorrelation corrected or consistent standard errors, but be informed that this is valid only for large samples, and we should be knowing this as well, that this procedure it can be applied very easily in Eviews. Now going back to the original slide, so for pure autocorrelation we studied 4 remedial measures that can fix the problem of autocorrelation. Now the next step is the application of these methods in Eviews. Now moving toward application of remedial measures for autocorrelation, I would like to remind you that we did task 13.1 till 13.4, the 4 tasks which we did. I will quickly refresh your memories on that in first task we regress log of consumption on log of real disposable personal income, real wealth, real interest rate, and we use USA data from 1947 till 2000 for these variables. So we did this function estimation in task 13.1. then subsequently in 13.2, 13.3 and 13.4 we use graphical method, Durbin-Watson d-statistic and BG-LM test for detecting autocorrelation in this model. And from all these tests, we concluded that there is a positive autocorrelation in this particular model, which we estimated earlier. Now, the remedial measures. So there are a number of remedial measures that we can use for fixing the problem of autocorrelation. We start with the first difference transformation. Then we can think of using the guessing of rho, the autocorrelation coefficient, by either using Durbin-Watson d-statistic or using the error terms of the regression model. And in either case, we will get the rho value, and then this rho value can be used to transform the original model to a new model that will be free from autocorrelation. So we will see that how it works. And then we can also use HAC or Newey-West approach for fixing the problem of autocorrelation. So I'm going to start with for the first difference transformation remedial measure for autocorrelation, and then subsequently I will be discussing the rest of the methods as well. So moving toward first difference transformation, this is practical task 14.1. in this we are going to solve the autocorrelation problem using first order transformation. Recall our task 13.1 in which we regress consumption on disposable personal income, wealth and interest rate, all in real form. So we concluded that there is positive autocorrelation. So now we are going to use the same model, but now we will fix the model for autocorrelation problem using first difference transformation. So this method is pretty simple. In this method, all we do is to regress the original. We use the differences of all the variable instead of original variable, and we use without intercept model. That is, we are going to estimate this model delta log of consumption in period T being regressed on delta log of disposable personal income plus delta log of wealth, real wealth, and delta real interest rate. So what does delta shows? Delta shows the variable in its differences. Delta log of consumption is equal to log of consumption in period T minus log of consumption in period T minus 1. So I would remind you that we did saw this. If I remind you, this was the first difference transformation in which we use the transformation equation and plug in the values of rho is equal to 1, and then we had this yt minus 1, and the the intercept term becomes 0 and the explanatory variable was also in the difference form. So we use the same regression model. We are going to use this regression model. We theoretically know that this model would be free from autocorrelation, and we then apply this model in Eviews and we will see the result. So in simple words, instead of using the original model, we use this difference model, and we will see that the problem of autocorrelation will be solved when we use this model for estimation. So to do this in Eviews, we have to estimate this model. Now this model can be estimated by a number of ways. As you can see that the variables are in difference form. So for that we need the log of the variable, then its lag values, then its differences. So there could be a number of ways through which we can estimate this model in Eviews. The first way, which will be very obvious, is to take log of all the variable. So I have consumption variable, I will take the log of consumption, then I will take the log of disposable personal income, log of W, log of R, then I will take their first leg. So I will take the log of consumption leg, then the log of disposable personal income leg, then the log of W leg, only real interest rate leg, and then I take their first differences. So I, in a way, derive these four variables separately by doing each step individually and then formulating these variables and then finally running the model. So that's the first way of doing it. The second way is that I can directly generate the required log differences variable by running this formula. If you look at this formula, in this formula, log of variable will take the variable log value. So for example, if I write log of consumption, it will give me log of consumption. Similarly, if I generate a variable log of DPI, so it will give me the log of DPI. So that's straightforward. Then if I take the differences with that as well, so it will automatically take the first difference, like it will automatically give me consumption T minus consumption T minus 1, log of consumption T minus log of consumption T minus 1. Similarly, if I write here DPI, so it will give me log of DPI T minus log of DPI T minus 1, and similarly I can derive the other two variables as well. So this can be shown here. The second way can be shown here. You can derive the delta consumption variable, which I named as delta underscore consum is equal to D, that's for the first difference, then within bracket I wrote log, and then I wrote the variable. Please make sure that you write these brackets correctly. If you do that wrong, you will get error. Similarly, you derive delta DPI, delta W, that will be done through generate new variables. So finally delta R is just dr because it is without the log form. So that's the second way of doing it, slightly quicker way of doing this model. And then we can run, once we have these variables being generated, then we can run this model. The third way of doing is that we can directly estimate this model. If you are slightly expert, so you can then directly do this model. In that case, you can run this model directly as shown here. You can see here that delta log of consumption being regressed on delta log of DPI and delta log of wealth and delta R. So either you derive these variables individually and then use it in the model, or you can directly write this for them, opening the original variable as a equation and then writing this equation. It will give you the same model. It doesn't matter, it's your choice. Whichever method you use, at the end you have to run this model and you have to estimate your regression model in first difference. So now I would request you to pause your screens and do apply this method, and please obtain the results for this model, and then we discuss it further. Okay, so I presume that you have done that by yourself. Now I will switch to Eviews to show you that how we can do that while estimating this model. So this is my Eviews screen. As you can see, I have the consumption, I have disposable personal income, I have real interest rate, and I have the wealth. For simplicity, I will remove this time and year so that to make it more easy for me. So now I have to, as I said, there are a number of ways through which I can run the difference model as shown on the screen. So I will first try the first method. In the first method, we go for creating the log variables individually. So I will go to object, generate series. So I'll go for generating log of consumption. That should be equal to log of consumption. Similarly, I will go to object, I will go to generate series, I will generate ln dpi, that should be equal to log dpi. Then again I go to generate series, and this time I generate ln r, no, not r, ln w. So ln log of w. So I have these variables generated, then I need the lag of each of these variables. So I will go again, I will take the log, so object generate series, I will call it ln consumption underscore lag 1, that is equal to consumption. Sorry, I will ln consum and minus 1. So it will take its first lag. Similarly, I will take the first lag of the dpi as well, log of dpi. So I will call it ln dpi lag 1 should be equal to ln dpi within bracket minus 1. So it will give me the first lag of dpi. Similarly, I will need to generate the log of w lag 1. That should be equal to w within bracket log of w within bracket minus 1, and press OK. And now finally I need to have the lag of r as well. So it was without it's without log, so I will do it without log. So r lag is equal to r minus 1. So now I have these variable consumption, log of consumption, consumption lag, dpi lag, and log of dpi lag, then log of wealth lag 1, r log of r lag 1. So all are done. I will make this log of r1 so that it is consistent. Okay, so now I need consumption lag, log of consumption minus log of consumption t minus 1. So for that I need to generate the first variable, which I called delta consumption. That should be equal to ln consum minus ln consum underscore lag 1. So this gives me the first difference of consumption variable. Similarly, I generate another one. I will call it delta underscore dpi. That is equal to ln dpi minus ln dpi underscore lag 1. Similarly, I generate delta w, that should be equal to ln of w minus ln of w underscore lag 1. Finally, I generate delta r should be equal to r minus r underscore lag 1. So now I'm ready to run this model. All I have to do is that I will select delta consumption, delta DPI, delta W, where is delta W, and delta R. Open them as an equation. I remove the constant because it should be without constant. I press OK, and here is the output. Delta consumption being regress on delta DPI, delta wealth, and delta real rate. I wouldn't discuss the output. I will just freeze it. Keep it here for the record. I delete this. That was one way of doing it. The second way of doing was that we directly generate delta consumption using these formulas, which is displayed on the screen. So this could be done through direct formula. Let me try. So now we use the second way of doing it. That's the direct way of doing it. So for that, first of all, I will delete all the variable which I created. I will just leave consumption, DPI, consumption, DPI, R, and W. I will leave only these variables. Right, so now I'm going to do this through another way. In this way, I'm generating the series directly by using this formula, delta consumption is equal to, I take D, then within bracket I write log of consum, and then I double close. So what does it do? It will give me directly the delta consumption. First it will take the log, then it will take the first difference. So that will give me directly the first difference of the consumption. So I can do that. It gives me delta consumption. Then I can do the same for the DPI. So I write delta underscore DPI, that should be equal to D. Within bracket I write log DPI, and then I close both brackets. Similarly, I do it for the third variable, which is wealth. So delta underscore wealth, that is equal to D within bracket wealth, and then log, and then wealth, and then both bracket close. And then I do it for R. For R, I don't need a log, so I will directly do delta R is equal to dr. It will take its first difference. I don't need the log, so press OK. And then again, I open these variables as equation. Open as equation. I remove the constant because we didn't need the constant. I press OK, and I get the exactly same result as you can see here. That's the second way of doing it. I will again not discuss it. I will just freeze the output. I will leave it here. And now I move to the third part. So now we use this method to directly estimate this model instead of creating all these variables. So I delete all these variables which I just created a while ago. And now we do it directly. So indirectly, you select consumption, DPI, W, and R, open as an equation. All the variables are open as equation. This method is for experts, so I would not advise you to use it, but nevertheless, those of you who are good with Eviews can use it. So now I use D under within bracket. I take log of consumption, and then I take D. Within bracket I take log of DPI, then I take D first difference, then take log of W, then I take difference, and we don't need a log of R, so I just take the first difference of R. So this is the equation, D log of consumption, both bracket close, D log of DPI, both bracket close, d log of w, both bracket close, and d of r. Press OK, and if you see, all the three method gives me exactly the same result. Each number of these are exactly the same. So it is up to you whichever way is easy for you to run the first difference model. So once you run this model, then we go for the interpretation of the result. So please let me switch to my presentation to discuss the results. So the results, once we use the first order transformation, irrespective of the three methods, we can use either of the method to solve, to run the model, the first difference model. This was the result of the model, and as we see the results, there are a number of things we can see, but for time being we are not going for the interpretation. We are more interested in the problem of autocorrelation. So we already know that Durbin-Watson D statistic shows autocorrelation, and we can see here the value of Durbin-Watson D statistic close to 2. It's almost 2. So we already know that in Durbin-Watson D statistic value 2 shows no autocorrelation, 4 show perfect negative autocorrelation, and 0 show perfect positive autocorrelation. So the range between 2 and certain I think it was DL and 4 minus DU. So that is the range where there is no autocorrelation. So this value 2.02 is almost 2. So that's very close to no autocorrelation range. So we says that the problem of autocorrelation has been solved. To be more sure, we can apply the BG test and can see if there is a problem of autocorrelation or it has been solved. So let me demonstrate that as well, that how we can apply this BG test and see if this is still the problem of autocorrelation is still there. So let me switch to Eviews. So this was the results we obtained a while ago. So I will go for view, then residual diagnostic, serial correlation, LM test. I select one leg and I press OK, and I can see here the result of the BG test. As you can see, the F statistic with 0.3723 and chi-square with 0.82 cannot reject the H0, and H0 under BG is that there is no autocorrelation. So we cannot reject H0, and hence we conclude that the problem of autocorrelation is solved, or there is no autocorrelation in our model anymore. To sum it up, when we do the first order transformation, we use the differences of the original model, original variable rather than the original form, and this solve the problem of autocorrelation. We did that in Eviews and we saw that it do solve the problem of autocorrelation. So let me move back to my original slide from where we started all this discussion. So coming back to the result part, we can see here that the Durbin-Watson D statistic also shows that the problem of autocorrelation has been solved, and also that BG test shows that there is no autocorrelation problem. Now we can compare the output of the original model with the output of the difference model. Just to make a comparison, you can see here on the left side you have original model, and on the right side you have the differences model. The values are different, the signs are different. You can see here the R sign is different. Beside that, the R square value has been different, and R square in both models are not comparable because the dependent variable is not same. In one model you have the log of consumption, in the other you have the first difference of the log of consumption. So these are not comparable. You can see that DPI and W values are comparable for both value. DPI is 0.84 and 0.80 and 0.20 and 0.1. It's not a big difference, it's comparable values, but more importantly you should see the coefficients and their statistical significance values that has been changed a lot. You can see here the standard error in original model is quite low compared to the standard error in the difference model, and accordingly the T statistic value has been changed from very high significant to slightly lower significance. You can also argue on the sign which is different for R. This is statistically not significant, so in technical term it's not influencing the consumption. That's the most plausible explanation. However, there could be some other reasons for that as well. We may be getting the wrong sign because the row value which we have selected is not correct, or maybe because one of these variables are statistically, it's not stationary. We already I introduced this concept of stationarity, that when during the period of time the characteristics of a time series does not remain the same, we say that this variable is not stationary. By characteristics we mean the mean, variance and covariance of a variable. So with that, we are done with task 14.1. Let me go back to the remedial measure. So we were discussing the remedial measure of the autocorrelation. We already discussed the first difference transformation. We saw that how the first difference transformation transformed the original model to difference model, and how this difference model then solved the problem of autocorrelation. We applied it in Eviews and we saw it as well. Given the time of the lecture, I think I should stop here for this week. For this particular lecture, I will cover the remaining remedial measure and the remaining topic of this chapter in the next lecture. Thank you for watching. If you like our video, please do like, comment if you have any question, or send an email. I would also like if you subscribe my channel. Thank you very much.